Hi everybody, and this is Jim Corkins. We are now starting our fourth lecture, and this is called What is Acceleration? Okay, so we all know what accelerated motion looks like. Okay, but we want to reduce it down to simple terms, and we want to get the concept of acceleration and what it does right. Okay. So it all starts with this very first question, okay? So it is possible for an object to be moving to the right and accelerating to the left. It is possible for the object to be moving to the left and accelerating to the right. It is actually possible for an object to not be moving in an instant, but still be accelerating. And it is also possible for an object to have constant speed, yet still be accelerating. Okay, so let's do this red one together. Okay, and well, we're going to do all of them together, but I want you to think about this red one. How is it possible for me to be moving to the left but accelerating to the right? Okay, and I want you to think about it in a moment, and it's just like a person or a ball or a truck, not multiple objects, just one single object. How is it possible for that single object to be moving to the left but accelerating to the right? Okay, so try this on your own and pause the video now. Okay, well, let's talk about this. So we had learned that before that it is possible for us to have an object to have a positive velocity but negative position. And so we learned that position and velocity are two different things. Well, similar to that, velocity and acceleration are also two different things. They are related to each other, but they are conceptually different from each other. So let's go ahead and try to put this into something that we can understand. So let's say you're standing. Let's say your position is negative. Let's say your position is positive. So you have a positive position at 0 seconds. Okay. And your velocity is negative. So you're moving to the left, and you move to the left over the period of 1 second. You move -2 meters over that period of 1 second. Okay. All right. Now, velocity and acceleration are both vectors. Your velocity vector is which way you're moving and also how fast you're moving, right? Your speed. Okay. Well, acceleration is another vector. An acceleration vector, just like velocity, could be pointed to the right or pointed to the left, indifferent to velocity altogether. So it is possible for you to be moving to the left, yet your acceleration vector, so you're moving to the left -2 meters per second, your acceleration vector is going to be pointed to the right. And let's call that acceleration a +1 meter per second over the period of 1 second. So that acceleration vector is a velocity vector over the period of a second, right? So basically, acceleration is adding a velocity vector to an initial velocity vector for a period of 1 second. Okay, we often talk about acceleration as meter per second squared. But again, just like velocity, you have a -2 meter displacement over the period of 1 second. Well, acceleration is a +1 meter per second velocity vector over the period of 1 second. Okay, think of think of acceleration as a push or pull. You're moving to the left, and somebody is pushing you to the right. So you're walking to the left at 2 meters per second. All of a sudden somebody pops up and begins pushing you to the right at 1 meter per second for every 1 second, right? During that period of time, you are going to be slowing down. So this is slowing down. When your velocity vector and acceleration vector are in opposite directions, that is slowing down. Conversely, if I take the vector head of this and I make it now pointed to the left, that acceleration vector is going to be negative, which means this. You're going to be moving to the left and somebody comes up behind you and they begin pushing you to the left. During that period of time that they're pushing you to the left as you're moving to the left, you're going to be speeding up. So when your acceleration vector and your velocity vector are pointed in the same direction, that is called speeding up. Again, think of acceleration right now as a push or a pull. We're going to find out later on when we get to forces, acceleration is a force, but you have to think about the object's mass too. Okay, so that's the first two. This next one, when you throw an object up in the air, it's moving upwards and it's slowing down. So its velocity vector will look something like this. It'll be getting smaller and smaller and smaller and then smaller. Okay. Then something's going to happen. It's going to come to a stop. So its velocity is going to be equal to 0. Now it's going to turn around and begin falling down and speeding up. So at this instant, the entire time, if you're moving upwards and you're slowing down, that means there has to be an acceleration vector acting on you at each one of these seconds and making you smaller, bringing you to a stop. And that acceleration vector, which is called gravity, constantly pulls down on you at 9.8 meters per second over the period of 1 second. So it's pulling down on you. It's adding a 9.8 meters per second velocity vector down for every 1 second. So during that instant where you reach the top, you still have that acceleration vector adding on you that moment that you came to a stop. Okay, when you throw a ball in the air and it comes to a stop and then it begins to speed up as it comes back down, gravity doesn't turn off. So that for that instant, you're not moving and you're accelerating down. This is called a turnaround. So when you have a velocity vector, when you have no velocity vector but an acceleration vector, that can only happen when an object is going from moving upwards and turning around to moving downwards. In that one instant between up and down, it had to come to a stop. Yet there is an acceleration vector on you. This next one, notice I use the word speed. So I use the word speed. And we're going to get more into this towards the end of class when we get into circular motion. But when you are moving in a circle, when you're turning in a circle, and let's say you're going clockwise, so we're looking down on you, you're driving in your car doing donuts, your velocity at each one of these points is at a tangent to that circle. So how do you go from moving upwards to moving to the left? Well, somebody had to push you towards the center of that circle. How do you go from turning left to turning down? Somebody had to push you towards the center of the circle. Okay, so you're going upwards, somebody pushes you to the left, now you're going to the left. If you're going to the left, somebody pushes you down, you're now going down. If you're moving down and somebody pushes you to the right, now you're moving to the right. Somebody pushes you upwards, and now you're moving upwards. So this is a centripetal acceleration vector. Whenever your velocity vector, let's use blue for velocity vector. If you have a velocity vector pointed to the right, and you have an acceleration vector that is perpendicular to that velocity vector, this acceleration vector will only turn you left or right. Since it's perpendicular to your velocity vector, it cannot speed you up nor slow you down. For that to happen, the acceleration vector has to be parallel to your velocity vector. Okay? So this is what is called a centripetal acceleration vector. It's a vector that turns you. So this is going to be turning. It's going to be turning you clockwise or counterclockwise. So I put these questions up here just to let us all think about things and let us really think about what acceleration really is. Acceleration is a velocity vector that is being added to an initial velocity vector over the period of time of 1 second. So it's kind of like an additional velocity vector, right? Another type of velocity vector, acceleration vector, is one that is responsible for turning you. So an acceleration vector, which is a push or a pull when it's parallel to your velocity vector, that's going to speed you up or slow you down. But if you have an acceleration vector that is perpendicular to a velocity vector, it's going to turn you clockwise or counterclockwise. Okay? So that's really how little we really know about acceleration. And so, as such, I don't want us to think about acceleration as accelerating or decelerating. We're going to use simple terms like speed up, slow down, constant velocity, turning clockwise, turning counterclockwise. Okay? But this is what linear acceleration is. So we're, right now, until the end of class, we're only going to be dealing with velocity vectors and acceleration vectors that are parallel to each other. This would be speeding up while moving to the right. This would be slowing down while moving to the right. Okay? So think of acceleration as a push or a pull that is working on motion. If you're moving to the right and somebody is pushing you to the left, you will be slowing down during that instant. And if you're moving to the right and somebody is pushing you to the right, you will be speeding up during that motion. So we're only going to deal with velocity vectors and acceleration vectors that are parallel to each other, where it's going to change your speed, speeding you up or slowing you down. So think of acceleration as coming from a push or a pull. Okay? And it's going to change your velocity. That acceleration is a change in your velocity. It's a difference in your final velocity. Your final velocity will be different. If your final velocity is, linear velocity is different from your initial linear velocity, well then your velocity changed. Your velocity changed, which something had to cause that, a push or a pull, and that is what acceleration is. So that's how velocity and acceleration are different from each other. They're two different vectors that are adding together or subtracting together, that is changing that initial velocity vector to a new final velocity. Okay? Before we get there, let's define speeding up, slowing down, and constant velocity while moving to the right or to the left, which is this part. So this part is here. if you have an acceleration vector that is positive, that acceleration, if you're moving to the right and somebody begins pushing you to the right, you are going to be speeding up while moving to the right. Similarly, if you are moving to the left and somebody begins pushing you to the left, you're going to be speeding up while moving to the left. However, if you're moving to the right and somebody's pushing you to the left, you will be slowing down in that instant while moving to the right. If you're moving to the left and your acceleration vector is to the right, you're going to be slowing down while moving to the left. So whenever your acceleration and velocity vectors are pointing in the same direction, that is called speeding up. Whenever your velocity vector and acceleration vector are opposite each other, that is called slowing down. Okay? And constant velocity is this. If you're moving to the right, so let's say you have a positive velocity vector in the x direction, but you have no acceleration vector, which means acceleration is a change in your velocity. Well, and that acceleration is neither it's adding 0 to your initial velocity, or so that means it's not changing your velocity. So this is constant velocity to the right. So you're moving to the right at a constant velocity. So that's when constant velocity is when you have a velocity vector, but no acceleration vector. Okay. This is going to be a negative velocity vector in the x direction, but again, you have no acceleration vector. So this is constant velocity. Misspelled that. Left. So these are the terms we're going to be using. Speeding up, slowing down, and constant velocity. Again, speeding up is when your acceleration vectors are pointing in the same direction. That means your acceleration vector is adding to your initial velocity vector and creating a new velocity vector. Okay. Slowing down is when your acceleration vector is opposite your velocity vector. So you're moving to the right and an acceleration vector is subtracting from that velocity vector. So the next vector will be a little bit smaller, just like we learned in the vector and addition and subtraction in one dimension. Okay. Constant velocity is when you have a velocity vector but no acceleration vector. So nothing is adding to your initial velocity, so your initial velocity is equal to your final velocity. Okay? All right. Let's look at how acceleration is going to change your motion. Okay? Well, let me expand this so you could see what I'm doing here. Okay, let's try this again. Okay. So suppose you had an initial velocity vector pointed to the right, and that the size of that was positive 1 meter per second to the right. And suppose you had an acceleration vector that was positive 2 meters per second for every 1 second. Well, your velocity vector is going to look like this. So let's try this. Here we go. So what speeding up will look like in a motion diagram is this. You start off with your initial velocity from right before you even start moving. So you're already moving at positive 1 meters per second at the 0 second mark. Now, what acceleration is doing is it's adding a positive 2 meters per second to that initial velocity vector to create a new velocity vector. Okay. So it's adding that positive 1 meter per second to your initial velocity vector. So it's adding a positive 2 meters per second velocity to your initial velocity vector and creating a new velocity vector of positive 3 meters per second. Well, now that is your new velocity. If we add positive 2 meters per second acceleration to this positive 3, your next vector is going to be positive 5 meters per second, which is how we got this. So the length of this is positive 5 meters displacement over the next second, from 1 to 2 seconds. Now this is your new initial velocity vector. If we add that acceleration vector of positive 1 meters per second for the next second, you're going to end up getting a positive 7 meters per second. A quick way to actually think about this. So that is what acceleration is doing. Okay, acceleration is adding a velocity vector to an initial velocity vector to create a new final velocity vector. Then that final velocity vector is a new initial velocity vector. You're adding that constant acceleration vector to it and creating another one. And then finally, you have your last velocity vector here that you're adding an acceleration vector to, and that is going to be a new velocity vector. So notice how your velocity vector is increasing by 2 every time. That's what this acceleration vector is doing. It's adding a positive 2 meters per second for every second to this initial velocity. Here is what slowing down looks like. Okay, so if you're slowing down, you're moving to the right. You start moving to the right at positive 7 meters per second. A second later, positive 5 meters per second. A second later, positive 3 meters per second. A second later, positive 1 meter per second. Okay, so this is what it would look like when you're hitting your brakes on your car. Really what is happening is you start out moving at positive 7 meters per second, and you're subtracting a negative 2 meters per second from that. Okay. And then when you do that, you walk to the right 7 steps, walk to the left 2 steps, and your overall trip would be from the right to the from the left to the right, positive 5 meters per second. So positive 7 minus 2 is positive 5. That is your new velocity vector. So you got positive 5 minus 2 meters per second. So positive 5 meters per second minus 2 meters per second is equal to positive 3 meters per second. Positive 3 meters per second minus 2 meters per second is positive 1 meter per second. And this would be your final velocity of the entire 3-second trip. Okay, so this is what acceleration is actually doing. It's adding or acceleration adds or subtracts a velocity vector for every 1 second to your initial velocity vector and changing the size of that. Okay. Well, since we learned about motion, okay, let's try seeing if you could spot what speeding, so here are 1, 2, 3, 4, 5, 6 motion diagrams, where the starting position is at 0. So this is just regular motion diagrams. In between each dot is 1 second. So for A, you've got 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. So each one of these motion diagram represents 5 seconds of motion. Where it says start, the object starts here. This one will be moving to the right. So it starts here at the 0 meter mark and gets to 50. Over here, C looks like it starts at positive 50 and is moving to the left until it reaches the 0 meter mark. Okay. So I want you to try this out. I want you to categorize A, B, C, D, E, and F as speeding up, slowing down, or constant velocity. What I also want you to do is categorize each one of these green vectors as positive or negative velocity. Again, positive velocity is to the right, negative velocity is to the left. Now, using those two pieces of information, we're going to be able to figure out the direction of the acceleration vector. But for now, let's not worry about the acceleration vector. Let's just type the motion as speeding up or slowing down or constant velocity. And the velocity vector is pointing to the right or to the left. So try this out for A, B, C, D, E, and F using this Excel spreadsheet right here. Okay, try it out. Pause the video now. Okay, we're back. So I'm going to move in on this. So we know that this object, if you look here, it's moving only this far over a period of 1 second. So it starts here. So A, all these vectors are pointed to the right. So first off, let's call that a positive velocity vector in the x direction. And the motion type, well, it's moving only this far in 1 second, and then later on it's moving this far in 1 second. So this looks like it's 5 times as big as this initial velocity vector. So that's like saying I'm moving at positive 1 meter per second, and then later on moving at positive 5 meters per second. Okay, which I would say that is speeding up while moving to the right. Let's try B. So B is all those green arrows are pointed to the right, so that is also a positive velocity vector in the x direction. And let's look at B. It starts out pointed to the right, really big vector. In the very end part, it's a really small vector. So this is like saying you start out moving at positive 5 meters per second and later on are moving to the right at 1 meter per second, for positive 1 meters for every 1 second. So this definitely is slowing down. Okay. C, well, you start here at the 50 meter mark. You're starting here and you're moving to the left the entire time. So C is a negative velocity vector in the x direction. And C starts out with a small vector that's negative 1 meter per second and ends up moving at negative 5 meters per second. So I'm going to just write those here. And this is negative 1 meter per second. This one would be positive 1 meter per second. And this is positive 5 meters per second. I should have been writing those the entire time. And this is positive 5 meters per second. Okay, so you start off moving to the left at 1 meter per second and end up at moving to the left at 5 meters per second. So negative doesn't matter, that's just a direction. So if you start out moving at 1 meter per second, end up moving at 5 meters per second, you're definitely speeding up. All right, D, all those vectors are pointed to the left, so that those are all negative velocities. And it looks like you start off right here at moving at negative 5 meters per second. And it looks like you're moving to the left at negative 1 meter displacement for every 1 second. So here you're moving at 5 meters per second and 1 meter per second. So you are definitely slowing down there. Now, E, all of these vectors are pointed to the right. And if you look at them, they're all the same size, which looks like they're all positive 3 meters per second. I'm just guessing that's the size of them. So since they all have the same size, the entire time, that is definitely constant velocity. Over here with F, you start out here, you're moving to the left at 3 meters per second. In the middle part, you're still moving to the left at 3 meters per second. And in the end, you're still moving to the left at 3 meters per second. So those are all negative vectors, and that is also constant velocity. Now, from those two pieces of information, I want us to figure out the direction of the acceleration vector. And I want you to think about it. Is the acceleration vector adding to this initial velocity vector to make it bigger, or is it subtracting to make it smaller in size? So think about speed up, slow down, constant velocity, those definitions which we just talked about, in relation to the direction of the velocity vector. And figure out the direction of those acceleration vectors as positive, negative, or zero. Pause the video now. Okay, well, for an acceleration vector, if you're right here moving at positive 1 meter per second, and then later on moving at positive 5 meters per second, your 1 meter per second velocity vector is being added to, so this looks like it's positive 1 meter per second, 2, 3, 4, and 5. So that's definitely getting longer, which somebody has to be pushing you to the right to speed you up. So this is speeding up while moving to the right. What this would look like in these sets of equations is your velocity would be positive. Your initial velocity is positive. This is a curve fit, and it looks like your starting position is going to be 0. So in this one, you start at 0, so this guy is just 0. This velocity vector is pointed to the right, and those acceleration vectors are both pointing to the right. We'll learn more about these equations. We're going to learn that on a position versus time graph, they're going to be rounded, which is curvilinear. Okay? So this is how we're constructing equations. The directions of those vectors are what I've learned. Most students have a difficulty with picking those out. So those two equations are describing speeding up while moving to the right. Okay. Let's try out the next one. Let's try out B. Well, B is we're moving to the right. We start out moving to the right at 5 meters per second, and we end up moving to the right at 1 meter per second. So that 5 meters per second is being reduced by 1 for every 1 second. So that is definitely a negative acceleration vector. What that would look like is your acceleration vectors in both equations would be negative. Your velocity vector is going to be positive, and your starting position right here, which would end up being 0. Okay, because this starts out right at the 0 mark. Okay, so let's try the next one. Let's try C. Well, C says you're moving to the left the entire time. You start out moving to the left at negative 1 meter per second, and now you're moving to the left at negative 5 meters per second. So your acceleration vector has to be adding to your velocity vector to make it larger over time. Since your velocity vector is negative, you're being pushed to the left, you'll be speeding up, which means your acceleration vector will be negative. Your velocity vector is also negative, and this position right here, since we started out at the positive 50 meters, is actually just positive 50 meters. Okay? We're creating equations. Okay, let's try D. D starts out, you're moving to the left at -5 meters per second, and you end up moving to the left at 1 meter per second. So that means something had to be pushing you to the right the entire time as you're moving to the left. So your acceleration vector is going to be positive. So this is a positive acceleration vector in both cases, although you're moving to the left. And you started out moving again at the positive 50 meter mark. Okay, that's the start, positive 50 meters. Okay. Let's do the last two. Those are both pretty easy since your velocity is not changing in either case. You could say those acceleration vectors are both 0. So for E, your acceleration vector is going to be 0. So this is not going to exist at all in both equations. Yet you're going to have a positive velocity in the x direction, and your starting position here is going to be 0 meters. Okay, now if you look at this right here, x final equals plus velocity times time plus 0. That is a linear fit. So when you're not speeding up nor slowing down, constant velocity is a linear fit. And what that also means in a velocity versus time graph, that your final velocity is equal to your initial velocity because there's nothing modifying speeding you up or slowing you down. Similarly, while moving to the left here, your velocity vector is going to be negative in both cases. But you started out moving at the positive 50 meter mark position. So again, this is a linear fit to a position versus time graph. You start out moving at positive 50 meters, so you would start up here, and then you're moving to the left, so your position is decreasing over time, and you end up at the positive 0, well, positive 0, that's just 0, over the period of 5 seconds. So that would be the linear fit. In a velocity versus time graph, your final velocity, again, is equal to your negative initial velocity. Okay, moving right along. This is one of your tutorials. And I think I'm going to leave it for you to figure out. But let's try the first one together. Okay? Now, below here is a number line, and those are your positions. Now, you're supposed to decide if the object is speeding up, slowing down, and constant velocity, just like you did, but here you're only reporting the velocity vectors and acceleration vectors. Again, to the right is positive, to the left is negative. So for part A, if you start out here and you're rolling down the ramp of A, rolling to the right down segment A, it looks like segment A are all negative positions, so your position is going to be positive, but your velocity vector, you're ultimately moving to the right, so that's going to be a positive velocity vector in the x direction. Now, what are you doing? Speeding up, slowing down, or constant velocity as you're rolling down the ramp? Well, you'd have to be speeding up. And if that's true, something is pushing you down the ramp as you're moving down the ramp. Okay? Skip over B, let's talk about C. Now, B and C are all positive positions. So we know our position as we're rolling up the ramp, we're skipping B, you can figure out that one, it's frictionless. So you're rolling up the ramp in C, So your positions are all positive. And you're still moving to the right as you're rolling up that ramp, but you're going to be slowing down as you're rolling up that ramp. That means your acceleration vector has to be negative. It's subtracting from your velocity vector and making it smaller over time. So go ahead and try this tutorial out and see how you do. Okay? And that ends what is acceleration. I hope you enjoyed it. I will hopefully see you later.